Section 5.7, we are going to look at infinite geometric series. So if you click on the link in Google Classroom, it will take you to the investigation on Desmos. We'll start with this warm-up. On the first day it was posted online, a music video got 600 views. The number of views that the video got each day increased by 20% per day. How many total views did the video get over the course of the first 23 days to the nearest whole number? So first you have to figure out, is this an arithmetic or geometric situation? And since it's increasing by 1% per day, it will be a geometric situation. And so if you recall the two formulas for finding the sum, the geometric one has the ratio. So it's going to be the second one right here. And then it says select the correct answer. Let's set up the formula. Give me a second here. I'm just going to pop up my iPad. Okay, so we know that we want the sum of the first 23 days, and it is geometric, so it's first term, 1 minus the ratio to the n power over 1 minus the ratio. And we have to figure out what the ratio is. So here the ratio is increasing by 20% per day. So change the 20% to a decimal, 0.2, and add a 1. And the 1 would be 100% of the views the day before plus the 20%. So 1.2 is our ratio. And we start with 600 views. So let's pop that into our equation. Let me change colors here. So the sum of the first 23 days, again, we start with 600 views. 1 minus our ratio at 1.2 for 23 days over 1 minus our ratio. And then when we type that in, I guess I'll pull up my calculator here, which will take another second. Okay, so let me type it in here. So we start with 600 parentheses, 1 minus our ratio, 1.2, to the power of 23 for 23 days. I like to hit enter, and then divide by 1 minus the ratio. And we'll see that after 23 days, so almost a month, that music video has a lot of views, 195,742. Oh, there it is. So we would select that one right there. So there's the power of exponential growth. All right, the pie problem. So, Miss Bayesian, me, I love to eat pie, and I don't like to share. Let's say I went to Perkins, and I ordered a French silk pie. I went home, and I ate half of it. Wanting to make the pie last, I only eat half of the pie that remains each day. Can we record the amount of pie that I eat each day? That's the top row. And then the total number of pie eaten over the course of that many days in the bottom row. So amount per day on the top, total amount on the bottom. So on day 1, I started with 1 whole pie, but I ate half. Oh, it doesn't show up very well, does it? Oh, it does. No. And total amount eaten is 0.5. I wonder if I can do fractions. Oh no, I deleted that. This is amount each day. Too bad it doesn't show that. Okay, so I can say 1/2, or I guess I could have put the 0.5. Okay, it changes it for me. So this is 0.5. I wonder why it does that. I'll just change it to 0.5. Okay, so the next day I eat half of a half, or 0.25. But if I add a quarter plus half, I've eaten 3/4. Okay, here's what I'm going to do. In class, I like to show it with fractions, so I'm going to show it with fractions as well. So again, here's our table, and now I can write it out. So we have the amount per day. Let's make it a little bit smaller than that. And this will be the total. And let's do it for a week. And then here's day 1, day 2, day 3, day 4, day 5, day 6, day 7. All right, so on the first day, I eat half of the pie, and then there's half left over, and half I've eaten total. The next day, I eat half of a half, which is 1/4. And if I add together 1/2 plus 1/4, when you add fractions, you need a common denominator. So when we have 1/2, and if I multiply that by 2/2, I get a common denominator. So another way to write 1/2 is 2/4. So 2/4 plus 1/4 is 3/4. So on this day, by day 2, I've already eaten 3/4 of the pie. Okay. The next day, I eat half of a fourth, and that would be 1/8. I've eaten 1/8 of the pie. And if I add 3/4 plus 1/8, again, I need a common denominator. So I'll multiply 3/4 by 2/2 and get 6/8 plus 1/8, which will be 7/8. So by the third day, I've eaten 7/8 of the pie. The next day, I'll eat half of 1/8, which is 1/16. And you might start to notice a pattern. Notice this is 1/2. This is 3/4. This is 7/8. So the numerator in the bottom row is always one less than the denominator. And the denominator is the same as the amount eaten per day. So like 1/2, 1/2, 1/4. The bottom is a 4, but we've eaten 3/4 and so on. So the pattern that we've noticed is, okay, this is 1/32, 1/64, 1/128, and then the pattern is the numerator is always 1 less than the denominator, so this would be 15/16. This would be 31/32. This would be 63/64, and this would be 127/128. So you can see by the end of the week, I mean, if you've eaten 1/27 out of 1/28 of a pie, you've eaten pretty much the whole thing. So that's kind of the patterns that we're looking for this table right here. I wonder why it doesn't let us do fractions. What if I type in 1/8? Oh, now, changes it. What was it, 16th, 1/32. This is 1/64. This is 1/128. But then if we type in, so this was 7/8 of the pie that I've eaten. This was 15/16 of the pie. This was 31/32. And you can see I've eaten like pretty much all of the pie, probably by day 4. This is 63/64. And this is 127/128. So you can see, again, you've eaten, by the end of the week, almost all of the pie right there. How much will Miss Bajan end up eating? Pretty much the whole pie. Ooh, there's a picture. Fresh raspberry pie. Yum. All right. What can we add up? Is it possible to add up all the numbers of a geometric series? So when we looked at, if we consider this total amount eaten, you can see that when we add it up, it ends up being almost the whole pie. So let's take a look in this problem. Let's go back to the zombie problem with the strain where a zombie walks into school, infects 1 person per day. Okay, this is a different strain than the one we talked about just a few days ago. So infects 1 person per day. Each new zombie can infect 1 new person per day. Here's the sequence of total zombies. So pretty much the number of zombies doubles per day. So 1 the first day, 2 the second day, 4, 8, 16, 32. Let's practice writing the explicit formula for this sequence. We can see this is geometric. So we can say A sub n. So for any day, the number of zombies will be the number of zombies the first day times, because it's being multiplied by 2 every time. to the n minus 1 power. So I'm going to do shift and then 6 to get that caret key, and then n minus, oh, it doesn't like that, so I have to put that in parentheses, n minus 1. All right, so there's the explicit formula. For this particular problem, I guess I didn't need to write a sub 1 because I can see that that's one zombie. So I can submit that. There's our explicit equation, that's geometric. First term times the ratio to the n minus 1 power. All right, and here it is graphed. Will the total number of zombies ever reach a limit? Does it ever level off, or will it keep increasing forever? And we can see that it's just going to keep doubling. It's going to keep increasing forever. Okay. A geometric series is called divergent when the ratio of the series is greater than 1. All right, so that zombie problem is divergent because the ratio is 2. We can see that it just will keep increasing if the ratio is 2 because it keeps doubling forever. Will a divergent series have a sum? Will it add to a number like 1 whole pi? And we can see if we're just doubling all the numbers in our sequence, it's not going to add up to one number. It's just going to keep getting bigger. So no sum. The terms just keep getting bigger. This problem right here, so here's my pi problem. I started with 1 pi and I ate half per day. Oops, I forgot my n minus 1 here. This is called a convergent series, which happens when the ratio is less than 1. Why do you think the series is called convergent? And you can see what happens is I keep eating more and more of the pi, and eventually there's no pi left. So here are all the terms in the sequence. And what happens is it's convergent because since these numbers approach 0, when we're adding the numbers together, eventually we start adding zeros and our number stays the same. So if we add zeros, which we can see that the numbers in our sequence would eventually go to 0, the sum would stay the same. A convergent series has a sum, like Mrs. Bajan's pi problem. So again, when we add up how much pi each day, eventually it's going to add up to that 1 whole pi. So we can use the sum of a partial geometric series. So again, we've looked at this formula before to explain how we can get just a number answer. So it says as n gets really large, n is the number of terms, the ratio gets really small. So again, if I take 0.5, which was my ratio for the pi problem, and I take it to the 100th power, like after 100 days, I'm eating very little of the pi left. So what happens is that ratio goes to 0 as n gets really large. The ratio will get really small, and then it eventually turns to 0. And what are we left with? We're left with this first term divided by 1 minus the ratio. And that's our formula for the sum of something called an infinite geometric series. So when we can find the sum of a series, it's this formula that we use if it's infinite. But we can only find the sum if the ratio is less than 1. Because if the ratio is less than 1, the numbers are going to decrease to 0. And we can add those numbers together. So here's an example. Find the infinite sum. And so how do we know when to find the infinite sum? It'll say add up all the terms from 1 to infinity. So that little 8 sign at the top of the sigma, the sideways 8, that means infinity. So you're going to add up all the numbers of the term, of the sequence, of the series, I should say. And when we look at it, we have to make sure we can actually add it up. And so you're checking for this thing right here, the ratio. If your ratio is less than 1, the numbers will get smaller and eventually become 0. And then we can add up all the numbers together. So this one will have a sum. Let's plug into the sum formula. And remember, the sum formula is this. First term over 1 minus the ratio. So I'm going to write that formula down. So this is for the infinite sum. It's first term over 1 minus the ratio. And so all we need is two things, the first term and the ratio. And that's actually given to us in the sigma notation. The first term is 8. And then the ratio is 0.25. So all we have to do is plug in 8 and 0.25. So the first term is 8, 1 minus, whoopsies. And so in our calculator, we would do 8 divided by parentheses 1 minus 0.25. A lot of you know that the bottom, 1 minus 0.25, that's the same as 0.75. Oops. Because it's like $1 minus a quarter. So if you wanted to save a few calculator keystrokes, you could just type in 8 divided by 0.75. And what do we get? 8 divided by 0.75. And we can see that eventually this is going to add up to about 10 2/3. 10 2/3. Or we could just say 10.6 if we rounded. Oh, it didn't like that. 2/3. Okay. So again, if we were to add up all the numbers in our list here, it would add up to about 10 2/3 because the numbers keep getting smaller and eventually reach 0, so we can add everything up. How do we find the sum of an infinite geometric series? So again, it's this formula, first term over 1 minus the ratio. You do have to make sure that the absolute value of the ratio is less than 1. So that ratio, again, has to be less than 1, or the numbers are going to just keep getting really big or really small, and you won't be able to add up the sum. So here's an example. A child on a swing is given a big push. She travels 14 feet total on the first back and forth swing, but only 3/4 as far on each successive swing. How far? What's the total distance she travels before the swing comes to a stop? So again, since it's only 3/4 of the distance every time, eventually it's going to slow down and stop, and we can add up all the distances. So here's our formula. Our ratio, 3/4 or 0.75, that's less than 1. So we know we're going to be able to find a sum. So all we have to do is plug in. So let me go to my work right here. And again, there's the formula. Let's just erase some of this. So here, the first term is 14 feet on the first swing over 1 minus 3/4, which is 0.75. So again, to save a few keystrokes in our calculator, that's the same as 14 divided by 0.25, right? Because it's like $1 minus 3/4 of $1, 0.75. So we can type that in, 14 divided by 0.25. And this is going to be the total distance that she travels back and forth, 56 feet. Okay, so let's put that in. 56 feet is what she travels, and you could submit that. Okay. Rebound height. Kimani drops a basketball from a height of 10 feet. Each time the ball hits the ground, it rebounds to 80% of its previous height. Can you draw a picture in your notes or on your whiteboard, representing the situation? So I'll use my iPad as like the whiteboard. Can we write the sigma notation, and can we solve? Find the total up and down distance the ball travels. Okay, so first the diagram or the picture of this, dropping the ball from a height of 10 feet. Okay. So here's the ball, and I'm dropping it from a height of 10 feet. So it goes down 10, but then it bounces up 80% of its original height. So if it bounces back up 80%, that's 80% of 10 feet. And of in math means times. And again, whenever you have a percentage, change it to a decimal. So this is 0.8 times 10, which is 8. So that ball will bounce up 8 feet, and when it bounces up 8 feet, it will also bounce down 8 feet, right? Because it will drop the same height. And then we need 80% of 8. So again, that's 0.8 times 8. And if we type that in, 0.8 times 8 is 6.4. So the next rebound, it goes up 6.4 feet. But then it's going to go down 6.4 feet. And then we could keep going. So if you notice, there's really two sequences here. There's the up height and the down height. So the down, it's 10 feet first, and then 8, and then 6.4, and then it keeps going. And then the rebound height, so the up or the rebound, starts at 8, and then 6.4, and then it keeps going. So really there's two sequences here that we're going to have to figure out the total distance and add up. And so when we go over this in class, some kids realize, hey, what we could do is this. Instead of coming up with two numbers and adding them together, like for the two different sequences, breaking it up into two problems, what you could do is you could ignore the 10 at first and just take a look at the sequences that start with 8 of them, and realize that there's two of those sequences, right? Up 8, down 8, up 6.4, down 6.4. And so when we write the sigma notation, we can say find the sum if it starts at 8 and it rebounds to 80% of its original height to the n minus 1 power, and it's infinite. So we start at the first bounce and we're going forever. All right, so there it is. But what we can do is we can find this, and this would be like the purple or the orange. But once we find that answer, that sum, we can just double it, because every time it goes up, it goes down that same amount. All right, so here's what I'm going to do. I'm going to double. I'm going to find out everything in that box, dot, dot, dot. It keeps going. And so here's our formula. So to find the sum, the infinite sum, it's first term over 1 minus the ratio. And here our first term is 8. Our ratio is in the parentheses, so 1 minus 0.8. All right, so I'm just going to type that in. You can either type in 8 divided by 1 minus 0.8 or 8 divided by 0.2, because that's the same as 1 minus 0.8. All right, so when you type that in, you should get 40 feet. Okay, so for one of the sequences, it goes all the way, like all the down distances are 40. But the rebound heights, if you notice, are the same, so it goes up 40 feet as well. And so we can say the total height would be this times 2. So it's going to be 80 feet. But then remember, we did add, or we need to add this initial 10 feet that it dropped. So we're going to take our 80 feet plus 10, and really that ball, so if you drop it from 10 feet and it rebounds up to 80% of its height each time, it'll travel a total distance of 90 feet before it comes to a complete stop. So this will be 90 feet. And then the sigma notation, again, if you write sum, it should pop up. 1 to infinity. Infinity. Ooh, look at that. It starts at 8, and it was 0.8 to the power of n minus 1. But then we multiply that whole thing by 2. Oh, I didn't like that. So times. Where's the times button? Times, so there it is, times 2. And then after that, we added 10. So there's one way that we could write that. So again, we figured out all the, like from the sequence starting at 8. We multiplied it by 2 and we added 10. Okay. Your investigation is complete. So really there's that one new formula, and you might see some review as well. So let's go back to the review. I think that was on the first slide. Okay, so far with a series, when you're adding up the terms, if it's arithmetic, we use this first formula, first term plus last term times the number of terms divided by 2. If it's partial, it's called a partial geometric series. So if you're adding up a certain number of terms in a geometric series, here's that formula that you use. But then if it's infinite, if you're adding up an infinite sequence, geometric sequence, and again, that's when it goes from 1 to infinity. If the ratio is less than 1, you can do that. And then here's the formula, which is first term over 1 minus the ratio. So your assignment will be to practice infinite geometric series. There's some new problems in there as well as some review problems in the assignment.